I'm really sad.
All right. So we're in section 13.8. And we're going to talk about relative extrema for multivariable functions. So for a single variable function, the extreme value theorem tells us that a continuous function obtains a maximum or a minimum, always obtains a maximum or a minimum on a closed interval. For functions of two variables, we have something similar. If we have a continuous function of two variables, it's going to have a maximum and a minimum value at least one point, rather than an interval in a closed bounded region. So we're talking about some region in the plane. Closed means it contains its boundaries, and bounded means it's a subset of a closed disk. So we're talking about some kind of region in the plane, and we have a boundary for that region. So in the extreme value theorem for a multivariable function says we're always going to be able to find a maximum or minimum value in that closed bounded region. So just to make it formal, let's talk about exactly what we mean by a relative maximum, relative minimum for a multivariable function. It's exactly how we think of it. I just want to make it formal. So we're gonna define a local maximum, relative maximum. So our function has a local max at some point AB in this closed bounded region if f of xy is less than or equal to f of AB for some open disk around AB. So this is saying that somewhere close around this point AB, that right around there, our function is less than the function value at the point. So that's that gives us a local maximum. And then we just turn our inequality around for a local minimum. So we're talking about what the function is behaving like nearby. So f of xy is going to have a local minimum. At our point, the point that we're interested in, if our function is greater than or equal to f of AB for some little area around the point AB. So that's what we mean by a local maximum, local minimum. We're just interested in how our function is behaving nearby. Critical points. We define critical points in a very similar way to the critical points of a function of a single variable. So our critical points, f of xy is going to have a critical point at AB if both of our first partials are 0 at that point. So if they are both 0, or if both partials or if our partials do not exist. So very, very similar to critical points of a function of a single variable. And we've already talked a little bit about this condition where our first partials both equal 0. We can prove, or it can be proven, that relative extrema occur only at critical points. So there's nowhere else. If we find our relative extrema, if we find our critical points, that's where our relative extrema can occur. And in the last couple of lessons, we talked about if f of x and f of y at a particular point both equal 0 at the same time. That tells us that our tangent plane is horizontal, because our gradient at that point is going to be the 0 vector. So every directional derivative at that point is 0, and every directional derivative is 0, our tangent plane is horizontal. So this condition that the first partials of x and y are 0 at the same time is the same as the idea that our tangent plane is horizontal. So the only place that this is going to happen, the only time we're going to get a horizontal tangent plane is at a critical point of our function. So I just want to make the connection or the analogy between single variable functions, multivariable functions, that we look for critical points. The critical points tell us where our relative extrema can occur, and that is also where our tangent point or our tangent plane is going to be horizontal, just like our tangent line would be horizontal at a relative extrema of a single variable function. All right, so I want to look at a quick example, and then we want to decide what kind of extrema we have, whether we have a maximum or a minimum. So I want to look at one example, and then we'll talk about how we figure out which of these we have. Any questions so far before we talk about an example? All right. Let's say we have g of x, y, and this is 9 minus x minus 3 squared minus y plus 2 squared. And we want to find any extrema. And I'm going to use a line from your textbook. You guys, was the last year that they used that textbook. We're going to be clever. So we want to find any relative extrema of this function. So we want to not work really hard. So looking at this, what do we know about x, the quantity, the sign of x minus 3 squared and x, or y minus y plus 2 squared? Positive or negative? Positive. We're subtracting both of those from 9. So what is going to be the largest value that this function could have? 9. And that's going to occur when x equals 3 and y equals negative 2. So our relative extrema are going to be at the point, any relative extrema is going to be at 3, negative 2. This function, what would the graph of this thing be? Dylan says this. So paraboloid, elliptical, but upside down. And 9 would be the value, the g value, the z value would be 9 at the vertex. And that would happen when x equals 3 and y equals 2. So that one's easy. But they're not always this easy, unfortunately. All right, so just like a function of a single variable, a critical point doesn't always give us an extreme value. For a single variable function, we could have an inflection point. For multivariable functions, we've talked about a little bit before, we end up with a saddle point. So saddle point is kind of a maximum, depending on how you look at it, it's a maximum one way and a minimum the other way. So an example of a saddle point would be on the function if we had f of x, y, z is 16x squared minus 9y squared plus 144z. We end up with a hyperbolic paraboloid. And then, so a hyperbolic paraboloid is a saddle shape. So we end up with a saddle point. And we have in order to figure out, do we have a saddle point? Do we have a maximum? Do we have a minimum? We need another tool. So for our single variable function, what was a tool that we used once we found our critical points? What was a tool that we used to decide if we had a maximum, minimum, or something else?
Derivative test?
So the derivative test, the first derivative test, is going to give us our critical points, right? And that's what we talked about before. Our first partial of x with respect to x, first partial with respect to y are going to be 0. Those are going to give us our critical points. But then to decide if we had a maximum, minimum, or an inflection point for a single variable function, what do we then do? Second derivative test. We have something like that for multivariable functions. That is the second partials test. Second partials test, a little more complicated than the second derivative test, but kind of the same idea. All right, so we're going to say that f, our function for our second derivative test, f of x, y, our second partials are continuous. So we want our function to be kind of well behaved. And it has continuous second partials somewhere around the point that we're interested in. So it doesn't have to be continuous everywhere, but we want it to be continuous around where we're interested in. And we have our first partials at this point AB are equal to 0. So we have a critical point. So we're looking at a critical point. We want to decide, is it a maximum, a minimum, or a saddle point? So we're going to let D, we call it our discriminant, f sub xx at this point times f sub yy at that point minus f sub xx at this point squared. So this is, xb, ab. So we find this discriminant at this point AB. Second partials with respect to x, second partial with respect to y, and this should be mixed partials, sorry, x, y. And our mixed partial squared. So we have three conditions. If D is positive and f sub xx is positive, then we have a relative minimum. Our second condition, if D is positive and f sub xx is negative, then we have a relative maximum. And if D is negative, we have a saddle point. And if D is 0, then we have to do more work. We can have where there's no conclusion. So we'd have to look at a graph or something, do some other kind of plug in points and see what's happening. We'd have to do some more work if D is 0. But if our functions are nice, well-behaved functions, usually we can get some kind of conclusion out of this discriminant. So this is our second partials test. We find our second partials at our critical point, and we find D, find our discriminant, and we check these conditions. This tells us whether we have a maximum, a minimum, or a saddle point. So nothing complicated. Find our critical points where the first partials both equal 0. And then we run our second partials test to see if we have a relative maximum, relative minimum, or a saddle point. And then tomorrow we'll talk about absolute extrema. And for an absolute extrema, then we add one piece to our search for the extreme values of our function. So questions here before we go on. So what we're doing is exactly like we did in Calculus 1 when we look for maximum, minimum values. We're just adding the details, adding the pieces that we need because we're dealing with a multivariable function. So I want to look at a couple of examples, just calculating, finding our relative extrema, running the second partials test. Okay, so let's say we have fxy is minus x squared minus 5y squared plus 10x minus 30y minus 62. And I wanted this to be 30y. HOX? Sounds like something with a model train, right? All right, so we want to find relative extrema. So that's our problem here, is to find the relative extrema of this thing. So we find our first partial derivatives, f sub x. We get minus 2x plus 10. This one's nice and easy. F sub y, we like it when there's only one variable here. Minus 10y minus 30. And we want these both to be 0. So we have a critical point. So our critical point is at 5, negative 3. Setting these equal to 0. Then we run our second partial test. So we need f sub xx. Second partial with respect to x is negative 2. F sub yy is negative 10. And f sub xy, mixed partial here, is 0. So d is negative 2 times negative 10 minus 0. So our condition here, we have d is positive, d is greater than 0, f sub xx less than 0. So f is our critical point, f of 5, negative 3. What does our second partial test tell us here? Relative maximum. So that one was easy. Sometimes the challenge in these comes from having to the simultaneous equations you have to solve to figure out where f sub x and f sub y are both 0 at the same time. That's really to find a relative maximum minimum. Usually that's where the challenge is if you have a complicated function solving those simultaneous equations. Sometimes you have to do some different things to solve your simultaneous equations. But then you run your second partials test at your critical point. Here our second partials didn't vary with x or y, so we just got nice numbers there. Any questions on that example? And let me look, let me double check here. I might have had a picture of that one. I forgot to pull it up earlier. I do. So let me pull that up and then we'll look at one more example. So I have a picture of this first function, graph of this first function. So this one was the first one that we talked about, where we were clever and we found our maximum there at the vertex. So there's our paraboloid, and there's the one we were talking about just now, and we found a critical point. What did we find? 16x squared. Is that the one I did? No, that's a different one. That's a different. Oh, that's our hyperbolic paraboloid that we talked about, where we end up with a saddle point. So that would be a saddle point there. We talked about the saddle point. Here's the one we just found. So we found this x squared minus 5y squared plus 10x minus 30y. So yeah, that's the one we just looked at. So we found the relative maxima right up here for that function. All right, let's do one more example where we have to do a little more work. All right, so we have f of xy is 2xy minus 1/2 x to the 4th plus y to the 4th plus 1. And we want to find our relative extrema. So these problems, just like finding maximums, minimums in single variable calculus, it's kind of nice because we always follow the same process, the same procedure. So we find our first partials. So our first partial with respect to x is going to be 2y minus 2x to the 3rd. And our partial with respect to y, we have a kind of a symmetrical situation here. So we have 2x minus 2 y to the third. Where do we have critical points here? We can pick out an easy one really quickly, can't we? 0, 0, where both of these are 0 at the same time. So we're going to have a critical point at 0, 0. So we'll need to run our second partial test for 0, 0. 0, 0 makes these 0 simultaneously. Can we pick out another one very easily? 1, 1. We plug in 1 here, we get a critical point. Any others? How about -1, -1? If 1, 1 works, does -1, -1 give us zeros? I get a -2 plus 2. So yeah. So -1, -1 would also give us a critical point. We could find these two by setting these two equal to each of these equal to 0 and solving simultaneous equations, and all of these would come out of those simultaneous equations. These are nice. These two equations are kind of nice because we can pick these out fairly easily. All right, so now we need to run our second partials test. So these, it was easy to pick them out. You can always solve simultaneous equations to find this. This one we could solve by substitution. Solve one for x or y, plug it into the other one. We could also multiply the top equation by x and the bottom equation by y and subtract one from the other to eliminate some things. So either one of those two ways would work for solving those, and these points would come out of that. All right, so let's run our second partials test. F sub x, x. Second partial with respect to x, we get minus 6x squared. Second partial with respect to y, we get minus 6y squared. And the mixed partial, f sub x, y, is 2. And we need our points here. So f of, we'll run the, let's run it for this. So f sub x at f sub xx at 1. For 1, 1, I get -6. Our second partial with respect to y at 1, 1, I get -6. So d here comes out to be 36 minus 4. So we get greater than 0. So at 1, 1, f sub xx is less than 0, d is greater than 0, so we have a relative max. And if I plug in -1, -1, I get the same exact values since I'm squaring. So this is going to be the same thing for -1. So we have a relative max at 1, 1. As well. So then we're going to run our second partials now for 0, 0. When we plug in 0 here, I'm going to say d of 0, 0. I get 0 minus 2 squared when I plug in zeros here. So I get -4. So d is less than 0. And that gives me what at 0, 0? Saddle point. So I have a relative max at 1, 1 and -1, -1, and I have a saddle point at 0, 0. So let's take a look at what the graph of this function looks like. There's what we're looking at. Let me make it a little bigger. So right there at 0, 0, right there in the middle is our saddle point, and we have a relative maximum here on either side. So that's a graph of that surface. That one's kind of interesting like this. All right, questions there? Okay. Now, just thinking ahead a little bit. Now we found we talked today about how we find a relative maximum minimum. When we talk about absolute maximum minimum, what are we going to add? What do you think we're going to add to our analysis? So when we talked about the absolute, think about a single variable function, we talked about the absolute maximum minimum of a single variable function. We had an interval that we were looking at. We found the critical points, and we always had to, and I remember I was thinking about this when I was looking it over this weekend, because I remember saying it over and over and over at Calc camp last year. Find your critical points and check the endpoints. We have to check the endpoints. Well, for a multivariable function, we don't have endpoints, we have a boundary. So we're going to check for our relative maximum and minimum on the interior of our region, and then we check the boundary. So we can end up with a maximum or minimum, an absolute maximum or minimum on the boundary of our region. So that's what we're going to add when we talk about this tomorrow. Okay. There you go.